Hi there, this is a comprehensive paper review on the paper Improving Intrinsic Exploration with Language Abstractions. This is a very cool paper because it combines a language and the information that is in language with reinforcement learning, specifically the problem of exploration. I don't want to tell you too much more right now because we're going to dive into the paper in just a bit. So this video will explain in detail what is in the paper, how the method works, what they're doing. So by the end of this video, you should have a really good idea of what's in the paper. In the next video, published tomorrow, there's going to be an interview with the authors of the paper, which is very, very cool. It's super valuable, and I was very happy to host this interview. So I hope you draw some value out of either one of these videos, hopefully both. As always, thank you very much for watching. Thanks to everyone who likes and comments and supports in any way. It's really cool to be able to do these things, and I'll see you around. Bye-bye. Hi there. Today we're looking at Improving Intrinsic Exploration with Language Abstractions by researchers of Stanford University, University of Washington, Meta AI, and University College London. This paper on a high level uses language to facilitate intrinsic exploration. That is when, in the face of a very sparse environment, a reinforcement learning agent has to come up with its own goals in order to make progress. So the intrinsic exploration or intrinsic motivation refers to the fact that there's an additional reward that we give to the agent just for attaining, let's say, new states, novel things in the environment. Now, it turns out that that's not super duper easy because not all new things are equal. And especially, let's say there is a random component in the environment, then, that's going to be new every time, yet it might not be interesting. So how you go about this is quite a challenge. It's clear that we need something like this in sparse rewards environment, but how exactly to do it is still challenging. This paper adds language to the mix and argues that language descriptions could be one such source of indicators of novel states. So we're gonna go through the paper. Let me know what you think in the comments, definitely. And yeah, let's dive in. So they say they want to solve these complex long horizon tasks with sparse rewards. And as I already said, that is not really a picnic for reinforcement learning agents. Usually those need very tight, very dense rewards in order to work. And that's why we give these intrinsic rewards for exploration. And that is encouraging the agent, even in the absence of rewards, to go out and explore things and do new things. And we hope that through the exploration, at some point it will learn the skills or it will encounter something that will actually give true reward. So they correctly claim there is a design choice on how to measure exploration and an implicit, like a common answer that the agent should be rewarded for attaining novel states in the environment. But that is, as we already said, quite difficult to actually implement. For example, states can look cosmetically different, but have the same underlying semantics and thus not be truly novel. So, the two fundamental challenges for intrinsic exploration they list here is, first, how can we reward true progress in the environment over meaningless exploration? Second, how can we tell when a state is not just superficially but semantically novel? And that's where they add in language. They say, well, if we had language describing the states, then certainly, for example, here we have language that describes the state. Here, the language description says in what direction, indicating that you can go in a couple of directions or do something in a couple of directions. You see here a crystal wand. That means there's something to pick up. So when you don't have this message, that might be an indication that the state is meaningfully different. Namely, it doesn't have the crystal wand. So as you can see, these authors imagine that if we had a language description of the environment, that could give us an indication of when something is novel and when something is just the same but looks a little bit different. They say language obviously has strong priors over the features and behaviors needed for meaningful interaction and skill acquisition. And that's just a matter of fact that language has been developed to communicate things that are useful to humans. And they also say correctly that you can describe with language very particular things such as move left, or very abstract things like acquire the amulet and defeat the wizard. Although one of the abstraction here comes from the and, but still defeat the wizard is a very, very abstract thing. Now, as we already said, what they're going to do here is they're going to look at these environments, at these reinforcement learning environments. So there's MiniGrid on the left. And in MiniGrid, I believe the agent here, that's the red triangle. And the agent is supposed to, I think, go to the keys, get the keys, open the doors, and eventually get the final reward that is somewhere on the map. These are procedurally generated, so it always kind of looks different. And that's one challenge, because if you have to make sequences of actions like go over here, get that key, go to the door, and then go further and get the reward, that is a sequence of actions that is unlikely to happen by chance, right? To stumble over the key and to stumble over the door and to stumble over the reward, the amount of times you're going to try randomly until that's the case is staggering. And therefore something like Q-learning, which just requires on random exploration, is going to almost certainly fail right here. But this is one of the environments, which is a challenging environment that they pick up, and that has these language descriptions, or I think in this one they add the language descriptions. But in any case, this is not about language models or anything like this. They assume that they have a function, which they call L, the language annotator, that takes in a state, and gives you the description. And they just assume they have an oracle that does that. So for the environments they do test, they actually have that. And so in MiniHack here, this is even part of the game, right? In MiniHack, you will always get a message like this to every step that you do in most of them. Most of these states have such a description available. So again, there's this function L, which in this case is just the game engine. It takes in a state and it gives you back the description. So if you could guess here that we might learn this language descriptor, right? We might even initialize it with a language model. We can use something like clip or something like this. This is certainly in the future work. They list this, but not here. Here we assume we have this oracle. Now, what can we do once we have such a language description? Well, we can use it for exploration. So there is a little bit of mathy math right here, which we're going to skip. Essentially, this just discusses that, they have this annotator L that produces these natural language descriptions, and they add an intrinsic reward to this. And now we're going to look at what the intrinsic reward is. So they're going to take two different algorithms that are already made for intrinsic motivation, and they're going to augment them with language. The reasoning behind it is that those two algorithms, the one is called AMIGo, the other one we'll get to in a second. They're already kind of state of the art in this domain. So what they say is if we add language to those and we can get a better result, then that kind of shows the usefulness of the language descriptions. So we're going to look at these algorithms briefly. Remember, these algorithms aren't by this paper. This paper is how to add language to them. So AMIGo, the adversarially motivated intrinsic goals, trains a student and a teacher. So there is a teacher that generates goals, and then the student is just a goal-conditioned policy. The goal is, as we said, provided by the teacher. So the student is the real reinforcement learner, but the student is simply conditioned on some goal that's provided by the teacher. It doesn't try to solve the actual problem. It solves the goal that the teacher gives it. I mean, it probably gets reward when it accidentally also fulfills the true reward goal, but it does get intrinsic reward. when it fulfills the goals set by the teacher. Now, the goal set by the teacher, that's the trick, obviously, right here. The teacher policy is quite smart. The teacher policy takes in the state of the student. So it looks at, where is the student? And it needs to now decide, what do I do? What kind of goal do I give the student? On the top left here, you see this in this MiniGrid environment. The teacher is this network or this function right here. It gives coordinates that the student has to get to. And then these coordinates, as you can see, they're I'm not sure if those are the actual coordinates, but whenever the student actually reaches them, so it provides the goal to the student. When the student reaches it, it gets reward. So that's it. There's also a notion of a difficulty threshold. That difficulty threshold is it increases during training. So the idea is that at the beginning, the teacher wants to suggest kind of easy goals. And then as time progresses, the teacher has to learn essentially how to make the goals harder and harder. And by making the goals harder, the student essentially has a curriculum of harder to reach skills. So the teacher should kind of learn to propose more hard goals. So I think that the work here is definitely done mostly by this teacher network and the challenges. In any case, there is this difficulty threshold. This difficulty threshold is increased linearly during training, and the teacher is given a positive reward if it proposes goals that take the student more than T star time steps to complete, and a negative reward for goals that are completed sooner or never completed within the finite time horizon. So it also can't go impossible, or it can't go too hard. It needs to go exactly as hard that the student reaches the goal, which means even if it's a possible goal, it can't go too hard for the current student. It needs to essentially propose goals that are just outside the abilities of the current student. So that zone of proximal development is kind of formalized in this teacher. That's AMIGo. So how do we add language to that? We saw that usually the teacher supposes or proposes coordinates for the student to get to. Now, if we have language descriptions for every state, so every state the student finds itself in, there is a language description. The teacher can simply output a language description of a state, right? In this case, these are formulated as kind of instructions, right? But remember, they are just descriptions as far as I can tell of the state. It is more evident in the MiniHack environment, right? So these are just descriptions of the state, whatever the game would output if you're in this state, and the teacher simply proposes these. So it just says, well, here is a goal for you. Try to get to a state where the language descriptor outputs that. So those are the goals that the teacher can choose. Where are we? Yep. So we don't have XY goals, but we have natural language goals. The student is rewarded if it reaches a state with the natural language description that the teacher outputs. Easy enough. So how does the teacher do this? It selects goals from the set of possible language descriptions in the environment. Now, initially, these are unknown. So the teacher doesn't know yet what the environment has in store because, again, we don't assume, let's say, extra information. We need to get out everything of the environment. Therefore, as we go through the environment, we collect more and more of these goals, and these are the goals that the teacher can choose. The teacher maintains a running set of goals that is updated as the student encounters new state descriptions. The teacher has this move to language, they say, creates a challenge. Not only must the teacher choose which goal to give to the student, it must also determine which goals are achievable. And that's why they train two different networks. There is a policy network, which produces the distribution over goals given a student's state. and a grounding network which predicts the probability that a goal is likely to be achieved in the first place. So remember, these environments, they're procedurally generated. So every time every new episode, I believe that's how it works, the student is placed in some environment that it has essentially never seen before. So now the teacher takes that in and it produces two things. It looks at this environment, produces two things. From the set of goals that it has, it picks one that it wants to propose. That needs to be, right? So it cannot always do the same. That's the interesting part right here. So if the green door is over here, go to the green door might be very easy in one environment, but very hard in the other environment. When I first read this, I thought, well, if the teacher knows no goals at the beginning, and it only collects these goals that the student encounters over the course of the episode, we're still kind of relying on random exploration of the student, right? Because any goal it hasn't achieved yet cannot be proposed. Whereas in the original XY coordinate, I believe at least, I can just propose any XY coordinate, like get to that. However, since this is procedurally generated, you might imagine that a student encounters like the green door in one environment where it's very easy. It essentially just stumbles upon it. And then in the next one, that's kind of a bit more challenging to reach. So we are still good on collecting goals. The other network it does is this grounding network. So the ground, let's call that GD, the grounding network, it gets the initial state and it proposes, it checks which of the goals are even possible to reach. So these are two slightly different targets. The policy, or let's call that the policy network wants to propose goals which it finds challenging enough, right, for the student to fulfill. The grounding network wants to check which of the goals are even reachable in the first place. The grounding network specifically is trained as this multi-class, they say a multi-label binary cross entropy loss, which I find to be a weird term, but okay. But essentially, it's given the initial state of an episode, we ask the grounding network to predict the first language description encountered along this trajectory, where T is the minimum T such that there is a description at all. So we're training the grounding network to predict the first language description term against all the other term in its encountered goals. This is kind of like a contrastive loss. So that first goal is certainly reachable from the initial state, and we simply take all the other ones as kind of a negatives for that first one. And exactly. So the second one can be seen as noisily generating negative samples of start state and unachieved description. Now, based on the set of descriptions known to the teacher. Now, this seems a bit weird, right, to train the grounding network like this. Like, what about the second text description that was encountered? That's certainly reachable too, no? At least I would guess so. This is really necessary, or maybe this here should be over goals that weren't encountered in the episode at all, right? But this seems quite weird to only take the first encountered language description as a positive example of this grounding network. Further, and let's go into criticism right after we conclude here. They say to summarize the teacher training the teacher involves 3 steps: updating the running set of descriptions seen in the environment. That's collecting the goals, essentially. Learning the policy network based on whether the student achieved the goals proposed by the teacher. Okay, that's the same as the original AMIGo. And third, learning the grounding network by predicting descriptions encountered from initial states. Okay, well, this description here I can agree with. I just don't see why only the first is taken as the positive sample. So what are we doing right here, and why? what I find weird is that this grounding network has to exist at all, right? In the original description, I don't know if these things are generated, if these, certainly all the coordinates exist, right, somewhere, but they're not necessarily reachable either for the original AMIGo. It seems weird that the policy network itself, whose goal it is to propose a goal that is just outside of the reach, essentially, of the student, couldn't itself make the determination of whether a state is reachable at all, because the original AMIGo network seems to be perfectly capable of making that determination for a set of coordinates, right? So it might, there is a difference in that something like go to the green door, there might be not a green door at all in the environment, but it seems a bit weird to split this stuff up into different networks, and it tells me maybe they tried it first and that didn't work, so they had to throw in kind of another loss, which is kind of a bit, not just a bit, annoying. But if it works with the extra loss, then okay. Here you can see again we have the AMIGo teacher. First it asks the grounding network what is even possible in this environment. Then that is relayed to the policy network or multiplied by the output of the policy network. Policy network predicts goals that the student in its current state could reach, but not under the threshold. All the while we add new goals, we train the grounding network on states that were actually reached during, right, what language was achieved during the episodes. We take the other ones as negatives. And then lastly, the policy network is trained like AMIGo. Now there is a typo here, I believe, because here it says the reward is given if the goal is achieved in less than T star steps, but I believe it should be more. I believe this should be more, because that's what it says in the text. Yeah, so that's that. Yeah, I don't know why the split. So the important difference as well is that the policy network is trained essentially with reinforcement learning, right? It's I guess an actor-critic framework, and it's trained on the action that it actually output, like in classic reinforcement learning fashion. Yet the grounding network seems to be more achieved in a classic supervised sense, just as an online classifier. I'm not sure if they have done ablations. I haven't seen the ablation of what the AMIGo does without the grounding network, but it would be interesting to see. The second, so here you can see how they add language, right? They add language by essentially replacing that teacher-student relationship where the teacher proposes goals in coordinate. Now the teacher proposes goals in language. So that's the novelty here. The other one, the other algorithm is this novelty algorithm. So the novelty algorithm is a little bit different. It defines intrinsic reward to be the difference in novelty between a state and the previous state. So there's this notion of novelty, and we're not going to take that as itself. Like, we're not going to take the novelty and give the agent a reward simply for achieving whatever we call novelty, right? And we can define novelty in whatever way we choose. What we do is we give the reward if the agent transitions from a state of low novelty to a state of high novelty. Okay, and so that's this thing right here. The max with 0 is so that this cannot be negative, so we don't penalize going from high novelty states to low novelty states, because sometimes that is necessary. And we also only give that reward if a state is encountered for the first time. So here the agent is encouraged to find new states because it only gets rewards when it encounters new states, and it is especially encountered to find new states that are a significant increase in novelty from the previous states. This is one way. What this avoids, I guess, is to get stuck in this loop. Yeah, let's say you're in an environment, right? And you're in an environment, and then here is like some random thing. People usually they say there's a TV with static on, like just kind of like shh, or there's a bunch of leaves flowing around or something like this. And the agent that is just going for novelty would just indefinitely stare at it. And this prevents it, because whatever you call novelty, if you call this novel, like a TV with static, because it's essentially a random signal, so it's super duper novel. However, you wouldn't get a reward for consecutively looking at the TV, because you would already be in an equally novel state, going to a new novel state, and that will give you no reward at all. So you're encouraged actually to go away from the TV, go somewhere else where you can transition from a low novelty to a single high novelty state. All right, so yeah. What they say is, in the first term, the n is the novelty. This quantity describes the difference in novelty between successive states, which is clipped larger than 0. This is written a little bit weird. This quantity here refers to the first term, not to this thing right here. This thing is just an explanation of what's in the term. So n is the novelty, and the reward is the difference in novelty. The second term, right, only if we encounter it for the first time. And how does this thing track novelty? This is an interesting concept. How do we how do we know if a state is novel? Sometimes it is sufficient, they say, to track exact state visitation counts. But obviously, as soon as the environment gets larger and a bit more complex, this is not possible anymore. So what do? We use this random network distillation. And I have to say, I have never heard of this, and it seems quite smart. So what we do is we have a state, again, so your agent is here, there's a bunch of walls and so on. What we do is we have a random neural network. Now that's always the same, but it is essentially random. So we take the state, we feed it through the random neural network, we get out some vector. Just some vector, because it's a randomly initialized fixed neural network. It's going to be some kind of embedding of that. Not a useful one, but just some sort of an embedding. And then what we do is we train a, what do they call it? We train a state embedding network. So let's call that E. We train embedding, again, this one takes this in, and it tries to predict this vector, right? It tries to predict it. Now, obviously, it can't see the weights of this neural network. Otherwise, this would be quite useless. But it tries to predict this vector, and it is trained. So the E is trained with backpropagation, while the blue one is fixed. Now, the logic here is that if I encounter a new state, right? So here's my new state. Agent is here. There's just one wall here. There's like a door here. I put it through both. I put it through both of these. New color. I put it through. I put it through this one, and I put it through this one, and then I get a vector here, and I get a vector here. I look at the error between the two, right? So what's the difference? If the error is small, I can safely assume that I have seen states like this before, because if the error is small, it means that this thing has learned to match this thing for some kind of similar state, right? We know that neural networks generalize well if they have training data in the same vicinity of the data that you want to test on. Therefore, if the states are quite close, that means the outputs are quite close. That's a property of random neural networks. If you don't change the states much, it depends a little bit on parameterization. But essentially, if you change the input a little bit, the neural network's output will change a little bit. And therefore, if you've encountered states like this before, this E would be trained on those states, would actually learn to match the blue fixed network's output, and therefore the distance here would be small. However, if the state is super novel, that would not have been like anything in the training data, and therefore this E network would make a large mistake when trying to predict a vector. And from that mistake right here, because you have that at inference time, right? You can determine whether something is novel. There's a bunch of caveats, but since this paper isn't about novelty itself, I'm gonna reserve that for another time. So what do we do? To add language, that's this paper now, we add an additional exploration bonus based on novelty defined according to the natural language description of states. So again, this is simply a repetition of the formula. We have some sort of a notion of novelty of a linguistic description, and we give the reward if the novelty of the new state is higher than the novelty of the old state for whatever definition, and only the first time we encounter it. So they say NL is the novelty of the description L as measured by a separately parameterized random network distillation network encoding the description. So presumably, other than inputting states, now every state also has a language description. So language description here, language description here. We have a separate network, a separate random network that we can put them through. And we also have a separate embedding network. Let's call that EL, the language embedding network. And we do the exact same thing with the language as we did with the states themselves. We try to train this EL in order to match the predictions of the random network. If at inference time the two match closely, we assume that this is like something we've seen in the training data, and otherwise it's novel. So here you can see they say we keep the original exploration bonus as language rewards may be sparse. So they add both. The intrinsic reward is the original one that is just about the state, and the new one with a hyperparameter. And here, I think it becomes clear what, for me, the biggest criticism of this paper is. And that I think, so they make the point that, well, language helps. And if you look at the experiments, they say linguistic exploration outperforms non-linguistic exploration. That's one of their experimental findings. You can look at the results, although the confidence intervals, like this is just reinforcement learning, I get it, but you had to work hard to make those, to make these overall intervals not overlap. That is, good job, but still, the noise in these environments is quite significant. And linguistic exploration excels in larger environments, which you can imagine, right? Because in larger environments, they might be also more complex environments, and therefore just state abstractions themselves might not be the best one. But my criticism here is that essentially they add extra data, right? So it's not like linguistic exploration outperforms non-linguistic exploration. It's, hey, the environment actually has this data right here, and no one's used that. So people just have used the image or whatnot, and the actions and the rewards, and there's this extra data. What if we use this extra data? Oh, we get better. Wow. And the data is obviously very good because it's made by humans, and the game creators have essentially, so the game creators know which states are equal, right? They code the game, and in the same vein, they produce these language descriptions. So the language descriptions are almost like a little bit of a view into the internal state of the game code itself, right? Even if that weren't the case, language obviously is quite powerful, but I get their argument that, language gives you abstraction, yada, 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 and so on. However, I think the gains here aren't language is better than, not language, because I don't think it's necessarily a fair comparison. It is, adding more stuff, adding more information, especially really good, really high quality information like they have, is better than not adding that information. Now, obviously, it matters what they do with the information. But I think a lot of the gains simply come from the fact that they add something on top. So, not to say like for example, in AMIGo, they drop the original teacher, right? But in this novelty, they don't even drop the original intrinsic exploration. Yeah. So, it's essentially really extra data that they add. What is interesting is that they analyze the curricula that emerge, right? It's given that it's language, you have a pretty good idea of what's happening over time. And they have these nice analyses right here where, for example, first the teacher proposes open the door before it proposes open the colored door. So see, here is a variable that holds a color. So you can see that the teacher first proposes the easier goal of opening any door, and then it proposes a lot of opening colored doors. It then discovers keys, going to the keys, picking up keys, then going next to the door with the key, and after it goes through the door, it picks up the ball, which is the final goal. So you can see clearly that as the training progresses, the teacher gives more and more complex goals. And that is kind of true. It's true for AMIGo and this novelty. It is not that true in all the environments. For the NetHack environment, I believe it's a little bit more, they call it a little bit more exploratory, in that it just tries to explore a lot of stuff, which is also good, right? That is, it doesn't need to be progressive, right? As long as the teacher encourages the student to, do this, and now you're really good at that, so I can't essentially propose that anymore because you'll fulfill it in less than the threshold time steps. Now, do something else. Now do something else, and do something else. Again, these aren't the descriptions, right? These are meant to be descriptions, not instructions. So this here, I guess, is a better example. So you want to reach a state that has the description of there is a staircase up here, right? So you just tell the student, please reach any state with that description. And you can see how this develops, which is pretty cool. The last thing they do is something that I also find very, very interesting, in that even though, as far as I understand, and I think they say this somewhere, they don't use pre-trained language models or anything like this in here. They do obviously output language and so on, so they need some sort of language model, but they don't make use of any pre-training on any external data or anything like this. Yet still, the semantics of the language seem to be captured a little bit. For example, they do this experiment where they replace all the language goals with unique identifiers. So go to the red door would just become token 1. Go to the blue door would become token 2. So now there is no shared substrings. So the model cannot generalize from this go to the door construction and sort of generalize the skills or generalize the reachability estimate of the goal. The result is one-hot goals perform quite competitively, which is good, right? So that lends more credence to what I say. Like, this is extra data, right? Then the second thing is the AMIGo is better able to exploit semantics with a more significant improvement in aggregate performance over the one-hot goals, in contrast to novelty, which shows less of a difference. So at least one of the methods is actually able to exploit these semantics in the language, and that is a promising outlook if we now want to go ahead and use something like pre-trained language models in these, or something like Clip to even get the description out of the state itself. That would be really cool, or some sort of a Clip modified for reinforcement learning, so we don't need to rely on environments which have this language description already built in, because very, very few do, right? And it seems to be quite hard to get, honestly, right? If we want to train a good model for that is challenging, right? If, let's say, Atari or so, very challenging you either need to collect labeled data for, describing Atari states, which itself is really hard. And if you let 3 humans do it, you're going to get 3 completely different descriptions. And at that point, we're going to need these large language models, because the large language models need to be able to tell, well, these 2 wildly different descriptions are actually meaning the same thing, right? And how much of a gain at that point is still left when all this noise comes on top of the learned description models and of the inferring whether 2 language descriptions are the same or not, whether or not there's still an actual difference there to like AMIGo and AMIGo remains to be seen, right? In this paper here uses a lot of oracles, right, to get its data, which is fine for research, but it's not necessarily means that this is going to be a practical thing in the future. So yeah, they say this though. They criticize themselves fairly well, I think. Say they want to alleviate the restriction on oracle language annotations, perhaps by using learned state description models. Exciting extension would be to propose abstract goals, which is also pretty cool, and again something where large language models can come in and help. Pre-trained ones even, right? You don't even have to train them. And using pre-trained, that's it stuck in my mind from reading it the last time. Pre-trained models to imbue semantics into the model beforehand, they say, would also be pretty interesting. Among a lot of other things, they also criticize the noisiness and so on. So that was it for the paper overview. Let me know what you think about this paper. I find it to be pretty interesting, and I think it's a really cool idea. And if we can extend this to not use oracles, I would be super happy. And I think this essentially is how humans also learn a lot of times, by talking about things, by talking about goals and so on. Language does provide a really good abstraction for these types of stuff. Yeah, let me know what you think in the comments. Leave a like if you do, and I'll see you around. Bye-bye.